Okay, welcome to this video. I'm going to go through a introduction to an experiment that sometimes is called Newton's second law experiment. I often call it Newtonian motion experiment. It basically involves, maybe I'll bring up a picture here. So we have a cart, a string, a pulley, and a mass. Now I'll go through the details, how I go about doing this experiment, but let's watch how someone else has gone about doing it. There's your pulley at the edge of the table. Some slotted masses at the bottom. So it starts off hanging. That's vital force.
1, go.
The weight falls. And there's your cart.
2, 1, go. 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 What's that for, Alex? What's this called? 2, 1, go. 2, 1, go.
So you get the idea. So in their experiment, they were letting that mass fall and they were adding extra masses to Now, the way I like to do this experiment is, alright, we've got two masses. We've got the mass of the cart and whatever else we put on there. We have a mass down here that's going to provide the weight force downwards, so that's what's actually pulling it. The system itself has a total mass of mt. The way I like to do this is I actually keep the total mass the same. So if this M2 is going to become heavier, then this M1 is going to become lighter, and I'll show you how that's done when we get to the method. So the system is accelerated by the weight of M1, so we have mg acting downwards, that's providing the force. And our total mass is M1 plus M2. We're going to ignore the mass of the string, it's insignificant. And the pulley, well, that just rotates around. Okay, so acceleration can be defined by Newton's second law as the net force divided by the total force of the system. And the net force is mass 1 times by g, that's the weight force. Let's look at the next picture. Alright, so acceleration then can be defined as m1g over total mass. You can write that as m1g over m1 m2, but I'm going to simplify this because the way I've done the experiment, at least the way I set up the theory, is this number on the bottom will end up being a constant. Alright, so the body, similarly to what you just saw there, is going to start from rest. So the initial velocity is 0, so I'm actually going to cancel this part out. And the way I go about doing it, look at this picture, is I've actually got a fixed distance I'm going to look at. Now that could be the distance all the way to where it hits there, but usually I measure this out as a fixed distance. Alright, so we can rearrange this equation of motion to become this. So t squared equals 2s divided by a. And then combining with this, in terms of the forces, this is the acceleration. We come up with a next equation. So putting those two equations together, t squared equals 2 times displacement divided by the acceleration. Simplifying that, t squared equals 2s mt over m1g. And no, I've got to write it this way. T squared equals, parentheses, 2s mt over g. Now I've mentioned that my displacement is constant and so is the total mass of the system. And g is gravitational acceleration. That's going to be a constant for our purposes here. And the two variables is time it takes to move through that fixed distance, starting from rest. And the other independent variable is going to be the mass at the bottom, or the hanging mass that's going to pull on the cart. So you have both, you have that and M2 in there. They do change, but they see the total mass is going to remain the same. So that's actually a constant. Now, the way I've written this, you have this part on the left-hand side. That's going to be our dependent variable in terms of how we graph this. We have this group of constants in the parentheses. We have the independent variable, which is going to be graphed as 1 on M1. Now, in this equation, we actually have a proportional equation. Imagine that you've got t squared is your y, and the constant slope, you say that's m, and we'll say times by x is the independent variable. Y equals mx. So variable equals constant times variable is going to be a straight line that goes through the origin. So the hypothesis will be t squared is proportional to 1 on m1. And what we should observe to confirm that is a straight line graph that goes through the origin. And using this, we can actually even determine a measurement for g. Now, let's go through the method. I wrote up a brief method, but then I let students determine how they're going to go about this. And I kind of let people loose on this. And we're going to use this also to explain errors because there was a lot of them. All right. So here's a little bit of a more detailed picture. So got my, I use the same. See, I've changed my symbols. All right, in that case, so M2 now becomes M1, like some of the other pictures we've seen. Never mind, just keep it consistent within your own equations, so that's fine. We'll come back to that later. So we set up the dynamics cart with a bit of mass on it. We measure out a distance. There's something there to stop it so it doesn't fall off the edge. And also we set up the solid mass with the string such that it doesn't hit the ground. Because we want, particularly throughout the motion, it's important that this solid mass is still falling as this is moving through the fixed distance that we want to measure. Otherwise, if it stops falling, if it hits the ground, then this stops accelerating. It will keep moving, but it won't be accelerating, and that's not going to be correct in terms of the variables. All right. So measure out the distance s. So I suggested 30 centimeters with masking tape. Place dynamics cart at far end, attach string such that the mass hung will not touch the ground as the cart moves through s. Moving on. Measure the time it takes to move through distance s starting from rest. Where you repeat this, so you go and do it again, and then again. I get 3 measurements from that same one. And what we're going to do, we're going to shift one of the solid masses, which are 50 grams each, so we use lighter masses than what we show in the video, from M2 to M1. Now, just consistent, that's M2 to M1 in terms of this diagram, which I've gotten, unfortunately, swapped out my masses. And then again, just go back to step 3 and repeat that. And then do this for 5 different masses. Now, from what I've seen in the data I've gathered, a lot of people had the dynamics cart itself weighed 600 grams. They started with just a dynamics cart, and the other group, the other mass was about 400 grams, and they just kept moving masses from M2 to M1 after they've done 3. So you would have a total of 1 kilogram for the total mass. So 600, 400, 650, 350, 700, 300. But in all cases, the total sum of the mass was 1 kilogram. You don't have to do it that way, but you need to pick a constant for that. Okay. The copy table of the book spreadsheet. Okay, we'll be going through the data analysis later, but here's something that you could use. All right. So we've got controlled variables are the s, the distance that you're going to let that move through, and the total mass. So, and then you can construct this table. All right. Just make sure you don't mix up your M1 and M2, because my theory is not the same as what I put in my method, so I'll repeat that again. All right, so that's going to be the end of this video. This was just the introduction. Next video, we're going to be looking at the data analysis. So we're going to see our results, and I'll show you how to go about doing this, how to analyze the results, how to construct the graph, and what to do with the graph. All right, signing out.